I'm going to discuss this theorem, which is known as the argument principle, which is basically if you have a meromorphic function, which means it's holomorphic, except it maybe adds a couple poles, and gamma is nice enough, then the integral of f prime over f, the logarithmic derivative, is just the number of zeros minus the number of poles. And I'm going to look at an example that will hopefully illustrate what's going on. I'm going to look at something with two zeros, both at 1, and 3 poles, all at I. And so I can compute the derivative by using the product rule. I could use the quotient rule, but I think the product rule might illustrate what's going on a little more. So this is a positive 2 just in case. So I can figure out f prime of z is equal to the derivative of the first thing times the second thing left alone, plus the derivative of the second thing, which is negative 3 times the first thing left alone, I to negative 4. And if I divide both these by f of z, that's going to be z minus I squared times z, or z minus 1 squared times z minus I to the negative 3. This is going to boil down, right? I'm going to get, oh, these two are going to cancel. So maybe they're going to cancel in red. And I'm going to be left with 2 over z minus I. Z minus 1, sorry. And then what's going to happen here? Oh, look, these z minus 1s are going to cancel, and I'm going to be left with just a z minus I to the negative 1 on top, which means I really have a z minus negative 1 in the bottom. And so if I take the integral around it, 2 over z minus 1 minus 3 over z minus I, this isn't too hard to figure out that this is going to be 2 times, maybe use the Cauchy integral formula, minus 3 times 2 pi I, or you could use residues, equals 2 pi I times 2 minus 3, which is the number of zeros, right, because I have 2 zeros here, 2 zeros here, minus the number of poles. That's the number of poles. So that's exactly what this theorem is saying. The theorem is saying is that this always happens. Let's move on to maybe a sketch of a proof of why this is. Alright, so here's how a proof might go. Alright, let's take a function, and let's suppose it has 2 places where it's 0. Let's call them a and b, and their multiplicities n and m. And then I might have some bit that has no zeros in g. So g definitely has no zeros. Well, right, if you compute the derivative, this is a giant product rule. Take the derivative of the first thing times the rest of it left alone times g plus the derivative of the second thing times everything else left alone. Oh, this should be n minus 1 to the n times z minus b. I'm taking the derivative of this one, so it's m minus 1 times the rest of it left alone, plus the derivative of the last thing, z minus a to the n, z minus b to the m, g prime. But remember, what I'm going to do is I'm going to divide this by f, because that's what I'm going to integrate over. I'm going to integrate by f prime over f. So if I divide all this by z minus a to the n times z minus b to the m times g, I can cancel. So I've got 3 terms on the top. I can cancel. Let's see what's going to happen. That's going to cancel with that for the first term. That's going to cancel with that, and I'm going to be left with n minus 1 divided by n. This is just going to give me z minus a. That's going to come from the first term. From the second term, I'm going to get, let's see, oh, all these z minus a's are going to cancel with all those. That g is going to cancel with that g. And then, oh, I'm going to be left with m, oh, plus m over z minus b. And then finally, I'm going to have, oh, that's going to cancel with that and that. I'm left with just g prime over g, where this has no zeros. So I'm going to pause here, and we're going to play this game again in part 2 of the screencast. So wait for that.